Alright, so you might be looking at this exercise and thinking, this looks a little familiar. And it should, because this is exercise 1.5.5. The only difference is that the notation is different. Instead of dealing with integrals of measurable functions, we're dealing with expected values of random variables. But expected values are integrals, and random variables are functions. So it's just the same thing. So I'm going to go through this exercise just so that we see the notational differences, but it's going to be the same exact proof. So again, we're going to start by writing each xn as xn plus minus xn minus, and we're going to do the same thing for x. X is x plus minus x minus. Since xn increases to x, xn is less than or equal to xn plus 1, which means that xn plus is going to be less than or equal to xn plus 1 plus. And the xn pluses increase to x plus. And so we can apply monotone convergence theorem to say that the expected value of xn plus will increase to the expected value of x plus. So next, since the xn's are increasing, the xn minuses are decreasing. Xn plus 1 minus is going to be less than or equal to xn minus. So for every single natural number n, xn minus is going to be less than or equal to xn minus 1 minus, which is less than or equal to dot dot dot, which is less than or equal to x1 minus. And so, if we take the expected value of xn minus is less than or equal to the expected value of x1 minus, which we know is finite. So we have a sequence of random variables xn minus. Each one has a finite integral, and these integrals are uniformly bounded by ex1 minus, which is a finite number, and they converge pointwise to x minus. And so we can apply the dominating convergence theorem with the dominating function x1 minus. We know that the exn minuses converge to ex minus. And since the xn minuses are decreasing, this sequence is decreasing because the expected values will decrease. And therefore, the expected value of xn is going to be the expected value of xn plus minus the expected value of xn minus. And the expected value of xn plus will increase to the expected value of x plus, and minus the expected value of xn minus will increase to minus the expected value of x minus. And this is precisely the expected value of x. And so we're done. So this is really nice. It's a good way to get used to using random variable notation, even if you've already done the theorem with integrals. And I don't know, I sort of like writing integral signs. They sort of look nice visually, but also this is a much easier to write proof because instead of having to write every integral and every d mu, you just have the letter e. And so this is nice, and so we are done.